Understanding frequency inverters, how VFDs work and why they matter. Welcome to the Control Brainiac, where we break down complex engineering concepts into clear, easy to understand videos. Today, we are diving into the world of frequency inverters, also known as variable frequency drives or VFDs. Whether you're an electrical engineer, an industrial technician, or just someone curious about how motors are controlled in everything from elevators to electric cars, this video is for you. Stick around as we explore how VFDs work, why they're essential in modern automation, and how they're transforming industries all over the globe. What is a frequency inverter? Let's start with the basics. A frequency inverter, or VFD, is an electronic device that controls the speed and torque of an electric motor by varying the frequency and voltage of the power supplied to it. Think of it as a dimmer switch, but instead of controlling light intensity, it controls motor performance. The main components of a VFD include a rectifier that converts AC to DC, a DC bus that filters and stores energy, and an inverter that converts the DC back to a variable frequency AC. By doing this, the VFD can precisely control how fast or slow a motor runs. Why use a frequency inverter? So, why use a frequency inverter instead of just turning a motor on or off? Here are some key benefits. Energy efficiency. By only using the power you need, you save energy and money. Motor protection. VFDs help prevent issues like overcurrent or overheating. Process control. You can ramp motors up and down slowly to reduce mechanical stress. Reduced maintenance, softer starts and stops mean less wear and tear. In fact, VFDs can reduce energy consumption by up to 50% in applications like HVAC systems and pumps. The VFD is to convert this AC into direct current, DC. This is done through a process called rectification, where components like diodes or silicon-controlled rectifiers, SCRs, allow current to flow in only one direction. As a result, the fluctuating AC signal is transformed into a pulsating DC voltage. Filtering, smoothing the DC. Now, even though the voltage is DC, it's not perfectly smooth. It still has ripples and fluctuations. That's where the DC bus comes into play. The DC bus is equipped with capacitors, which store energy, and sometimes inductors, which resist changes in current. These components work together to filter out the ripples and smooth the DC voltage into a steady, clean level. A stable DC supply is crucial for generating a high-quality AC output later on. Inversion. Creating variable AC output. This clean DC power is then fed into an inverter stage. Here, high-speed electronic switches, typically insulated gate bipolar transistors, IGBTs, are used to chop the DC voltage into pulses. These pulses are rapidly turned on and off in precise patterns using a technique called pulse width modulation, PWM. By adjusting the width, timing, and spacing of these pulses, the VFD can simulate an AC waveform of any frequency and voltage level. The result is an AC output that looks and behaves like a sine wave, but with a frequency that can be adjusted in real time, from a few Hz Hz up to several hundred Hz, depending on the system design. Longer equipment life due to reduced mechanical stress. In short, a VFD transforms fixed-speed AC power into customized, variable speed power, providing unmatched flexibility and control in a wide range of industrial and commercial applications. Applications of frequency inverters. Frequency inverters are found in almost every industry. Some common applications include pumps and fans in HVAC systems, conveyors in manufacturing plants, elevators and escalators, electric vehicles, CNC machines. In these settings, speed control isn't just convenient, it's often critical to safety, efficiency, and performance. For example, in a water treatment plant, varying the speed of pumps can precisely regulate flow and pressure. Types of variable frequency drives, VFDs. VFDs can be categorized based on their control methods, which define how the drive regulates the motor's speed, torque, and overall performance. Choosing the right type depends on the specific application, the level of precision needed, and whether feedback from the motor is required. Let's take a closer look at the three main types of VFD control methods. 1. Volts per Hertz, VOF, control. Also known as scalar control, this is the simplest and most cost-effective method of motor control. In this approach, the VFD maintains a constant ratio between voltage and frequency, e.g., 230 volt at 60 Hz, 115 volt at 30 Hz, to keep the magnetic field in the motor stable. Advantages: easy to set up and configure, inexpensive and widely available, adequate for basic applications where precise control is not essential. Limitations: poor torque control, especially at low speeds. No feedback from the motor, so it's less responsive to load changes. Not ideal for high performance or dynamic applications. Typical uses: fans, pumps, and conveyors where load conditions are predictable and constant. 2. Sensorless vector control, open loop vector. Sensorless vector control provides more advanced motor control by calculating the rotor position mathematically, rather than measuring it with a physical sensor. It uses internal algorithms and motor models to estimate real-time performance. Advantages: improved torque and speed control, especially at low RPMs. Better dynamic response to load changes. No need for an external encoder or feedback device. Limitations: accuracy may degrade under highly variable load conditions. Still not suitable for ultra-precise control or critical automation tasks. Typical uses: mixers, crushers, lifts, and other variable load machinery where improved performance is desired without the complexity of feedback systems. 3. Closed-loop vector control, field-oriented control. This is the most precise and responsive control method, often used in applications that demand tight regulation of speed, torque, and position. It uses an encoder or resolver to provide real-time feedback from the motor, allowing the VFD to make continuous adjustments. Advantages: high torque even at zero speed. Excellent control accuracy. Essential for automation, robotics, and positioning systems. Limitations: higher cost and complexity. Requires additional hardware, e.g., encoders, and fine-tuning. Typical uses: CNC machines, elevators, packaging equipment, and any process where exact motor control is mission-critical. Choosing the right VFD. The ideal VFD for your system depends on several key factors. Application type, e.g., fan versus industrial press. Load behavior, constant or variable. Control precision needed. Budget and complexity you're willing to manage. For simple systems, a VOF drive may be enough. For moderate performance without feedback, sensorless vector control is a strong option. And for high-end precision and torque control, closed-loop vector control is the best choice. Installation and safety. Installing a VFD isn't just plug and play. Here are a few key considerations. Always match the VFD to the motor size and load type. Ensure proper grounding and shielding to avoid electrical noise. Use line reactors or filters to minimize harmonics. Maintain proper cooling. VFDs generate heat during operation. And remember, safety is critical. Always follow the manufacturer's guidelines and local electrical codes. Troubleshooting and maintenance. Even with the best equipment, issues can arise. Common VFD problems include overvoltage or undervoltage errors, overcurrent trips, ground faults, overheating. To troubleshoot a VFD, always check the following: input and output voltages. Start by verifying that the VFD is receiving the correct input voltage from the power supply. Use a multimeter to confirm that the voltage matches the drive's rated input, whether it's single-phase or three-phase. Then, check the output voltage going from the VFD to the motor. If the output voltage is incorrect or unstable, it could point to issues with the inverter section, internal components, or even software configuration. Abnormal readings may also indicate that the VFD is in fault mode or derated due to overheating. Motor wiring and insulation. Loose, damaged, or misconnected wiring between the VFD and the motor can cause short circuits, ground faults, or erratic motor behavior. Inspect all terminals, cables, and connectors for tightness and signs of wear or damage. In addition, check the motor winding insulation using a megameter, insulation resistance tester. Low insulation resistance can lead to leakage currents, tripping faults, or even equipment failure. Ensuring solid electrical integrity between the VFD and motor is essential for reliable operation. Cooling fans and ventilation. VFDs generate heat during normal operation, so adequate cooling is crucial. Ensure that internal cooling fans are functioning properly. Many VFDs have fans that only activate above certain temperatures or when the drive is under load, so monitor during active operation. Also, make sure ventilation openings are not blocked by dust or debris. A clogged or poorly ventilated enclosure can lead to overheating, triggering thermal protection, reducing lifespan, or causing intermittent shutdowns. Drive parameter settings. Incorrect parameter configuration is a common and often overlooked issue. Parameters control critical aspects like acceleration and deceleration rates, maximum frequency, voltage limits, motor nameplate data, and protection features. If a motor is running poorly or not starting at all, double-check these settings against the motor specifications and the application requirements. Even a small mismatch in a parameter like base frequency or current limit can lead to underperformance or nuisance tripping. Most VFDs also store fault history. Review this log to identify recurring errors or misconfigurations. Always consult the manual. Each VFD model has its own layout, parameters, and diagnostics. Referring to the manufacturer's manual can save hours of guesswork and ensure that you're troubleshooting with accurate guidance. Regular inspections can help you prevent costly downtime and extend the life of both the VFD and the motor. So there you have it. Everything you need to know about frequency inverters and why they're a cornerstone of modern automation. From improving energy efficiency to enabling smarter machines, VFDs are here to stay. If you learned something new today, give this video a like, subscribe to the Control Brainiac, and hit the bell icon for more deep dives into the world of engineering and technology. Got questions or want to see a specific application covered? Drop a comment below. Thanks for watching, and as always, stay curious, stay powered.